Hey College Algebra. In today's video, we're going to be talking about applications of rational functions. So one of the things we're going to be talking about is this inverse variation, where you have two variables and their relationship is inverse of each other. And the other thing we're going to be talking about is where we see rational functions being used to maximize surface area given some volume. Some pretty interesting stuff, so let's go ahead and get started. So first off, let's talk about inverse variation. So let x and y denote two quantities. Then y varies inversely, this is the key word here, with x if there is some non-zero constant k such that we get this equation here. Now y and x are inversely related to each other, and so that's why we have it here in a denominator of a fraction, and k is some constant that we'll end up having to solve for to come up with specific answers to our question. So let's go ahead and look at an example where we're having to find some maximum weight when walking across a wooden board. So in figure 60, by the way, I just got this straight from the book, so it'll be problems just like it. On figure 60, we're going to be looking at this picture. The maximum weight W that can be safely supported by a 2 by 4 inch piece of pine wood varies inversely, that's the keyword that we're looking for, with its length L. And so just with that first sentence, we can set up some equation. We're always going to put some k on top because it's just some constant divided by L. Okay, so we've already got our equation. Good. Experiments indicate that the maximum weight that a 10-foot long pine, so 10-foot long pine, can support is 500 pounds. So here, if we plug 10 feet into our length and 500 for our weight, you can actually solve for k, but I want to continue reading on why this is important. Write a general formula relating the maximum weight W to the length L. Now, the reason why we need to set it up this way is that we need to solve for this constant k. Now, what we do, multiply this 10 over, and we'll get that k is equal to 5,000. Now we can plug k back into our original equation, and we get that our weight is equal to 5,000 divided by L. All right, but that's not quite the end of it yet. So find the maximum weight W that can be safely supported by a length of 25 feet. Now to answer this question, we just put 25 feet into our L here once we solve for K. And so W is equal to 5,000 divided by 25, which is just equal to 200. Therefore, the weight that somebody can be while walking over this is 200 pounds. Okay, so now I want to change paces a little bit. I want to find relationships where we'll end up using rational functions in a different sense. So before we go on to and start this problem, I want to just clarify a couple things. All we're going to be talking about here is maximizing surface area given some volume. And so here in this picture, I just break down how we find the surface area. And it's here, the surface area of this top bit, which is going to be pi r squared. And then in here, for the inside cylinder, all it is it's just a rectangle when you take it all apart. And so a rectangle's formula is its height times its width. And its width is equal to the circumference of a circle. And the circumference of a circle is just 2 pi r. And so our area of that inside bit is going to be 2 pi r times h. Okay. Now that we've just gone over that, I want to go ahead and read the question. So Reynolds Metal Company manufactures aluminum cans in the shape of cylinders with a capacity of 500 cubic centimeters. Okay, so our volume is going to be 500. The top and bottom of the can are made of a special aluminum alloy. It costs 50 cents. So the top and bottom are going to be made out of that material. And the side of the can is made out of material that costs only 2 cents. Okay, so here, what we're going to want to do is express the cost of the materials for the can as a function of the radius r of the can. Okay, so it's going to be a lot like maximizing the area given some perimeter. So here's our function for volume for a cylinder, and we know that volume is equal to 500, which is equal to pi r squared times h. And surface area, what that's going to be equal to is when we add up our top and bottom, our areas there are 2, because we have 2 of them, pi r squared. Now we just need to add in the surface area of the middle part of the cylinder. It's just 2 pi r times h. Okay. Now, the problem here is that when we're trying to express the cost of the materials of the can as a function of the radius r, we don't know, or we have 2 variables here. We have r, and then we also have h. And so we need to get h in terms of r. Now, before I do that, I want to go ahead and include one step. Here, our surface area for our top and bottom bits, we're going to multiply by 0.5. And that's because the cost of those tops and bottoms are 0.5. And the center is just going to be 2 pi r h times 0.02. Okay, now remember we wanted our surface area in terms of r, but here we have some h, and to put that h in terms of r, let's go ahead and look at our volume here. And let's go ahead and get this h by itself. So let's divide both sides by pi r squared. We'll get 500 divided by pi r squared is equal to h. Now let's go ahead and substitute this in for h. I want to pause the video and put this on another slide. Okay, so this ends up being our function for surface area. You get r's by itself, and when we multiply, when we put this h in, we'll end up getting a lot of cancellation. You cancel out these pi's and whatnot. So here, this became pi r squared because 2 times 0.5 is just 1. And then we add 20 over r. 2 times 500 times 0.02 is just 20. We cancel out the pi's, cancel out 2 of the r's, and we're just left with this r on the bottom. Now, we're just left with this function here. If we wanted to write this function in lowest terms, we need to multiply this part for a function by r, so that way it can have a common denominator of r. Now we can rewrite this as pi r cubed divided by r plus 20 divided by r, which is equal to pi r cubed. All right, and now if we want to construct this graph by hand, we can do that. But for right now, we're just going to stop here, and that was our solution to number 1. And number 2 is asking us, what r will result in the least amount of cost? Now, to determine this, we need to find the minimum in our graphing calculator. What I did here is I put our function and I put our function here into our calculator, and I changed r into x, and put it in for y1. Changed the window to get rid of all negative x and y values because it doesn't really make sense to have a negative x or a negative y, and then graphed it. Now to find the minimum here, so minimum, and you go to the left bound of this, and you go to the right bound and find the minimum. I'm going to go ahead and pause the video and do that. Now you'll get some value like this. Here it states that x is equal to 1.47, and that's actually going to be our minimum, or the r value that minimizes surface area. And the minimum surface area here is going to be 20.39 centimeters squared. And so you get that r is equal to 1.47 to minimize surface area, and the minimum surface area is going to be equal to 20.39. Okay, so we looked at a couple of applications of rational functions. There's a ton more, but next class we're going to be working with inverse variations and other situations where we're trying to maximize surface area. All right, see you guys next class.